All right, so last time we sort of concluded with this example of the Anscombe quartet, basically looking at these, quick refresher, right? There's these 4 different regressions that all looked basically identical, but then when we actually looked at the data, we could see that, you know, maybe they're not necessarily the best fit against that. So that was the point there, was kind of to make sure to look at that data. And so I wanted to do one last bit of sort of emphasis on the concept that we consider these metrics about the standard errors and the R squared, right? And having a good idea of what those actually mean, as opposed to, I think a lot of people just think about them as the sort of clearest indicators that your model is quote unquote good. So we're going to look at just one last example of this. Okay. So I'm going to copy and paste some stuff in here. So this is all stuff that you guys have seen before, hopefully at this point. So I need to, currently I'm putting it in a data table. So I'm going to load in data table. Okay, and just quick refresher, again, what we're doing here, random uniform distribution, doing this kind of error term, and then we have this equation on line 5, which is defining the true relationship between y and x. Again, this is not something that you normally would know. You'd usually just have your y and your x, and then you'd have to figure out this relationship, this 0.5, right, which is our beta coefficient, the slope of the line. And we can put in y's and x's in order to kind of try and determine that. And then there was a second example, which is identical to the first, except that we introduced like more noise. So the deviation is twice as large, okay? So this was that example where those points end up getting spread out. Okay. So to see kind of what that looks like, right? So plot x equals x, y equals y. And then AB line of example model 1. And we can compare that against the second example. Oh, what? I don't see anything wrong. What are you guys talking about? Okay. So let me run all of this really quickly. Oh, okay, so again, this is all stuff that we looked at in the last class. So here's our first one. And essentially, these are going to be identical. The main thing to remember here is look at the sort of x-axis range. So this is about -10 to about +30. The next example will have essentially the same slope, but it should be sort of more spread out. Yeah, so instead of -10 up to 30, now it's -20 up to 40. But otherwise, the slopes should be about the same. Okay, so instead of this time going into the summary to look at what the models have derived, what I'm actually going to do is something slightly different here. So I'm going to copy and paste a couple functions here. So this part, you guys don't need to kind of keep up with. This is more as a qualitative demonstration. And this will be posted online, so don't worry about that. What I'm actually going to do is instead of relying on the built-in LM function to calculate my standard error and my R squared, I'm going to do this manually. Okay, so you guys should remember, or actually you don't need to remember this, but these were shown last time, the equations for the standard error, which is y minus y hat. And so y hat is just x times beta. And that's divided by n minus 2 divided by the sum of x minus x bar squared, and then you take the square root of that whole term. So that's the equation for standard error. And all I've done here is to take that equation and manually put it into a function so that I can calculate for myself instead of relying on the LM. Okay, and I'm doing this for a particular reason. This isn't something that you guys will really ever have to do. And the same thing for the R squared. If you guys remember, the R squared is defined as, right, the difference between your y minus y hat squared divided by the comparison between the y minus the y mean. Okay, so you can see that defined here. And it's 1 minus this whole thing, and that gives you the R squared. Okay, so why am I doing this? We've got these two examples, one with the points closer together and one with the points spread out a little bit more. And the key thing here is that I know what the true value of beta is, right? Again, because I'm kind of acting as the sort of omnipotent, all-knowing person here, I have perfect knowledge of this guy, of the fact that the true value of my slope is 0.5. And normally you wouldn't know this, right? And so let's suppose I'm going to modify, let's say I guess incorrectly, and I say the beta is actually 0.45 instead of 0.5 for example 1. But for example 2, we'll keep it at the true value of 0.5. So let's look at these and see what happens. Okay, so nope, I didn't define it yet, sorry. Okay, so run that, okay. Okay, so in this case, for example 1, so that's x and y as opposed to y2, I have a standard error of 0.036 and an R squared value of 0.64. Okay, and that's using the incorrect beta value. Okay, and then in example 2, I have, let me pull this up a little bit so we can see both at the same time. Okay. Example 2, my standard error is twice as big, and my R squared is less than half of this. Okay. And this should be a word of caution here that just because your standard errors are smaller and that your R squared is larger doesn't mean that this model is better than this model. And in fact, we know that this model is actually correct, right? Because it's saying that the beta value is 0.5, whereas this one we know is incorrect. Okay, so again, these standard errors and R-squareds are a measure of something, right? And we should know what that means and interpret that as those things, as opposed to making some blanket statement that just because the standard errors are small and that your R-squared is big means that it's right. And we can directly know in this case, right, that's not the case. Okay. Any questions about that? Okay, so let me pull up the display then. Okay, so if the standard error and the R-squared aren't going to be, the main things describing, how good a model is, what other tools do we have at our disposal? And again, I want to sort of reiterate that it doesn't mean that you shouldn't use those things, the R-squared and standard error. They should just be part of a sort of broader toolkit to help assess whether or not the model is good. So we're going to look at a couple other things today. About how to assess the quality of a model. So the first one we'll be talking about is residuals. Okay, and so this is a concept that we've been actually talking about for a little while now, but we're gonna kind of see how we can leverage these in order to do some diagnostics. So this is simply defined as the deviation between observed and estimated values. Right, okay, so we have this equation, y hat equals beta x. Okay, and so remember that the little hat means that it is the predicted value. So this is like what's coming out of your model. And you calibrate this off of this term y equals beta x. So this will be something like this. So the residuals are this term, which is simply equal to yi minus yi hat. Okay, so these are your observed values, and these are your estimated values. So if I were to look at this in the data, it might look something like this. X, Y, and let's say you have a couple points here. So X. And let's say we have a line that looks like this. Okay, and so these might be some distance from my line. Okay, and so let's say this is distance of 1, 1.5, 1.5, 2, 1, something like that. I'm just kind of roughly eyeballing here. Okay, and this is going to correspond to what we call a residual plot here. So this is going to be my y hat. And this is going to be my residuals. Okay, so let's do something like this. And these will say at both at the same place. So let's say A, B, C, D. So then here we'll have A, B, let's say C, and D. So for point A on my y hat, here, let me just move this down here. So this is size 2. So we'll do 2, 1.5. So A would be here. B is at 1.5. So we'll say right around here. C is at 1 here. And D, we have 1 at 1, and we have 1 at 1.5. So this is known as your residual plot. And again, residual equals observed minus predicted. Okay, wait a minute. I just realized I did this totally wrong. This should be minus 1.5 and minus 2. Okay, so, all right, hang on. I'm gonna try this again. So let's do 0, -1, -2, +1, +2. Sorry about that. So A is at -2, B is at -1.5, C is at 1, and D is at 1.5 and 1. So it looks something like this. Okay, so again, this is kind of how you put the residual plot together. Yeah. This is y hat here. On the line, yes. Yes, you're right. I'm totally messing this up. Okay, yes. And this is actually this is actually why you don't do it on y, because you end up with biased. You'll end up with a biased plot here. Yeah. So yes, thank you for catching me here. I'm still making mistakes. So when you choose your ABCD points, it should be corresponding to the point on the line, not the point here against the actual observed. So this would be here, 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 and here. So this should be your like A, B, C, D, and then you can plot those here. Okay, sorry, I'm hopefully I'm not confusing people. Does that make sense? So these points will end up in slightly different places. Okay, so let's think about this sort of conceptually. If I have I'm going to draw two sort of residual plots. Okay, and let's say these are 0. Let's think about a plot that might look something like this. And let's think about a plot that might look something like this. Okay. Who can tell me any sort of inferences about these residual plots? What do you guys think about these guys? So I'll give you a hint. Like, think about, right, in the same way that you go from here to here, think about going from here back to there. And think about what the plot would look like for something like this. Yeah. Yes. Yep. Exactly. Okay, so let me draw what that looks like. So this is exactly right. And this is kind of what you want to take away from looking at plots like these. So let's say I have a plot that looks like this. So it's not going to be exactly, but hopefully you guys will get the point here. All of the residuals in this plot are positive, which means all of the points in my actual plot are above the line, right? Does that look like a good fit to you? No, right? So just by looking at the residual plot without even having any idea of what my actual observed looks like, I can tell you that there's probably something wrong here because of the sort of location of these points relative to my sort of 0 point here. Okay, now let's think about this one. What would this one look like? So here's my X, here's my Y. Let's say I have a line here. So we'll notice the first 3 points are negative, and then the last 3 points are negative, and they're sort of large negative going to smaller, and then small positive going to bigger positive. So maybe that looks something like this: big negative, slightly less negative, close to 0, small positive, getting bigger positive, right? And then eventually maybe coming back and then getting big negative again here. So that might look something like this. Okay, so does that look like a good fit to you? Probably not, right? Okay, so the sort of takeaway is that these residual plots are a really sort of nice diagnostic tool to see whether or not your estimate, this line, is biased in any way. And so the ideal residual plot would be kind of randomly scattered, but around 0, right? Whereas you're seeing patterns here. If you're seeing patterns in your residual plot, you got a problem, okay? It probably means that there's some bias in your model. Why is this useful compared to just looking at this? Well, this is just with a single X, right? One of the things I was saying is you should always try and visualize your data, okay? But as you have introduced more and more variables into your model, it's going to be harder and harder to do that, okay? And so you might miss the fact that, you know, one particular variable or the sort of interaction of multiple variables may start to do things like this, but you wouldn't be able to observe it because you couldn't visualize in multiple dimensions. But with the residuals, you can. The residuals is always going to be 2 dimensions here, where you can always plot your predicted against your residuals and see if there's something systematic about the errors. That's what you're looking for. Systematic errors that are showing up in your residual plot that then help you identify the fact that your model might be biased in some way. So this is a really handy tool that you can do in almost any regression that lets you sort of leverage this kind of visualization to identify possible areas of bias. Okay, any questions about this? Confusions? Okay. So I think this residuals and visualizing the residuals is one of the most useful ways of identifying systematic error in your model. So what are some other things that we can look at? Other metrics and tools to help diagnose your model. So this one is related. This is known as the residual standard error. And this is simply the standard deviation of residual values. So this essentially tells you the spread of the points about your regression line. Okay, so I'm gonna give the mathematical definition here, RSE. Again, this isn't something that you need to memorize, but as a reference, square root of 1 over n minus 2, summing y equals 1 to yi minus yi hat squared. Okay, it's just your residuals squared divided by n minus 2, and then take the square root. And oftentimes you can compare against the mean of the y value. Okay, so the residual standard error is a sort of helpful metric in some ways, but it's actually not all that common, I would say, to use this metric. But there is a sort of similar concept that is widely used called the mean squared error. So mean squared error, also known as the MSE. So this is something that we're going to be working with quite a lot. And this is used in diagnostics and certain techniques, all the way from linear regression to sort of complex machine learning algorithms. So we want to make sure we kind of really understand what's going on here. It's very similar to the residual squared error, but it's slightly easier to calculate. So I guess that's why people somewhat prefer this metric over the residual squared error. So this just looks like this. Okay, so I take my residuals here, I square it, and then I divide by n. So it is, right, the average of the squared errors. So think about this sort of qualitatively. If I have a line that goes through a bunch of points, and all of those points are really close to my line, this number is smaller, right? And the average of all of those little distances between my observed values and my estimated values are really small. And so then I have a small mean squared error. And if my line goes through a bunch of points and the points are really far from the line, this value becomes really big. And your average of all of those values will be large. And so this mean squared error will be sort of relatively large. The tricky thing about the MSE, though, is that unlike some of the other terms, so like the R squared, for example, which just between 0 and 1, the mean squared error is really context dependent, right? This could take on any sort of value. Like if you were doing a regression on, let's say, the GDP as one of your output variables, which might be in like billions, trillions of units, right? Then your MSE will sort of naturally be really large compared to a regression where your output might be, I don't know, something on the like in the decimal places, right? The MSE is context dependent on sort of the data that you're looking at. It is useful, however, to look at models that are comparing against the same thing. So let me give an example. So if you have y equals beta x1 versus the same y equals beta x2, right? Because your outcome variable is the same, when you do the comparison of the MSE, that is something that you can directly compare. So in this case, MSE comparison is good. But if you do versus z equals beta x1, MSE comparison is no good, right? Because you're using different outcome variables. This is a pretty rough rule of thumb. You need to think about the context of your problem to do direct MSE comparisons. But we're going to talk a lot about how we can leverage this in certain ways in the future. But just know that this is going to be a sort of really common metric that we'll be using throughout the course. Questions about the MSE? Okay. The last metric I'll talk about is one of the things that was showing up in the summary function when we look at the results for a regression. And this is the F statistic. So this is similar to standard error. And the hypothesis that all betas equals to 0. Okay, so in more sort of formal lingo, when we were talking about the standard errors, right? And we were talking about whether it's statistically significant and they have these like probabilities that you derive from these standard errors. That all has to do with the initial hypothesis of whether or not we believe the standard error, the value of the standard error is equal to 0. Okay, so if it's statistically significant, we reject that hypothesis because we say, actually, only a really small percentage of the time do we actually think that the slope of the line is 0. So the F statistic is basically like a standard error, but for all of the betas. So it's asking whether or not we think there's a significant chance that all of the betas are 0 or they have some value. So this is a really kind of high level way of saying, is our model actually useful in the sense that we think the slopes of our coefficients will be different from 0. And so when you only have one variable in the model, the F stat should actually be the same as our coefficient. It won't quite be in ours because we have the intercept, so there's something slightly different, but you can force the model not to have an intercept, and then you'll see that the F stat should be equal to the standard error. So I'll write the equation again, not something that you need to worry about memorizing. This one is slightly more complicated. Okay, so sum I equals 1 and I times y hat. Okay, so that's what the F stat is. Again, this is just for reference. You don't need to worry about manually calculating this. And then we'll talk a little bit more about the F statistic later on in the class for purposes of doing things like model selection, which will be coming in a couple lectures, I think. Okay, so let's jump on over to looking at some of these things in the code. Okay. So here we're going to use our original example 1, and I'm going to show something called the predict function. Okay. Predict is the function that gives you all of your y hats. Okay. So actually, I'm just going to go ahead and run this. And I get this like vector of points here. So can anyone tell me what these points represent? It's 100 points coming out of the predict function. So, all right. example model 1 comes from, right, running a regression. Let me pull that back up in the code. So that's way at the top here. Right. So we have X randomly generated points, Y generated from this relationship, same as before. We run it through a regression model, and you get some estimates of the coefficients. Okay, so this model has now created this line, right? And these 100 points that I got out of my predict function are the Y hats corresponding to each of the X's here. So if I were to, let's say, let me show this manually. Okay, so summary, example model 1. Okay, so we've got these numbers here, and let me see. So it was 100 points of X that I generated randomly. Let me grab the very first one of those. That's 37.86. Okay. So I have X I equals 1. So we know that this value is 37.86058. Okay, and then I have something like this. Y hat is equal to 0.47965, 0.47965 times X minus 0.48793. Okay, and so if I just take this X and I plug it into here, I should get some predicted value, which is, okay, 37.86058 times 0.47965 minus 0.48793. I hit enter. Whoops. I was like, that seems way too big. Here. Okay. I get a value of 17.6719. If I look at my predict of example model 1, and I look at the first entry of that, 17.672. It's the same thing. Okay, that's what the predict function is giving you. I have 100 randomly generated points. It will run this back through my equation and give me the Y hats corresponding to each of my X's. Okay. If I have my Y, so there's 100 points in Y, and I do minus predict of example model 1, what will this give me? What's Y minus Y hat? Residuals, perfect. Okay, so if I hit enter, this gives me all of the residuals. Okay, there's a shortcut for that. You can probably guess what that is. You can just do resid. Oops. So, okay, wait. Calculating residuals. So the first one way is Y minus predict of example model 1. And the shortcut is just doing this, resid of example model 1. So these, if I run this, it'll give the exact same vector values. It's actually doing that exact operation. Okay, great. So that's gonna let us look at the residuals. Let me actually go back for a second and mention something. So when you run the predict function, it by default fills in these like 100 values of X that you randomly generated. It fills in based off of the data that you generated from, or that you used to run the regression, okay? But you can do predictions on any number of points. So like, let's say you run a model and then you want to predict on a different set of points, you can do that here. So the way that happens is, let's do new X. X equals, let's just pick some random numbers here. Okay, and what I can do is predict example.model1, and then here I'll add an extra term. I think it's new data equals new.x. Okay, great. So we can see here that 4 numbers are returned out of the predict, and those numbers correspond to the new data that we're asking it to predict on. So at x equals 25, if I were to plug 25 into this equation, it will return 11.5 and then 13.42 and so on and so forth. So this is how you can ask your model to predict on like a new set of data. You just have to make sure that whatever you feed into it has to have data in the same form. So if I ran a regression of y on z, this actually wouldn't work. You have to have the name of the column be the same as what you ran your regression on. Okay. Let's see here. So I can look again, I can look at the plot of my residuals. And what we would want to plot is, so x equals y equals, so what would we want on our x-axis for the residual plot? Does everyone remember? Yep, yep. So we would do predict of example model 1, and then for y, we would do resid of example model 1. Okay, and I'll run this. And we see here kind of what you would want your ideal residual plot to look like, right? You just want random chaos sort of around 0. And if you're seeing anything else, if you're seeing like lines of dots, like patterns of dots, things above 0, everything below 0, all of these are indicators that there's some systematic error or bias in your model, and you probably have to do something, futz around with the model until you can get your residuals looking something like this. Yeah, you could have models with really good standard errors and really good R-squared, and when you look at the residuals, it'll be really obvious that that's not what you want. Yeah, for as something extra you guys can do, you could go back at the Anscombe quartet example, generate the residuals there, and you're going to see, you're going to exactly start to see patterns emerging that will be problematic. when you do a diagnostic with the residuals. Okay, let me see here. Okay, any questions about any of this so far? Great, okay. So I have actually tried to make the lecture a little bit shorter today so we could hop back over to doing our tutorial on visualizations and plots. So let's go ahead and do that. And I actually need to move some stuff around really quickly. One moment. This guy and this guy. Okay, so we are going to work with our coronavirus data set. So, okay, let me walk through this step by step, and then we will make sure everyone's kind of on the same page here. So I've already got data tables loaded, but I need ggplot. Okay, and I'm going to load in my coronavirus data set here. And before I do that, this might error out. I need to check where my directory is. Okay, so this will be kind of unique to me, but for you guys, right, make sure that you're setting your working directory to the same place where you have this file located. So I'm going to go ahead and do that on my end really quickly. So in here. And we're in lecture 5. And my last step, I will set that as my working directory, and I can already see the files here. Okay, so now that I've done that, I'm going to load in my data sets. And I'm actually going to load, actually, I'll do that in a second. So, okay, this is going to be kind of a repeat of what we were doing before. All I'm doing is essentially so if we remember the sort of 4 steps to doing the visualization, what I'm doing prior to even thinking about any of that is like prepping the data to be ready to manipulate and possibly also to plot. So, you know, there were some things that I wanted to change in the data set initially. And so one of those, I'm going to change the date format here to be as date. And then I am also going to do that procedure where I was able to look at, there was a column of cases and a column of deaths, and those were cumulative, but I also want the daily ones. So I'm going to do that thing that I did before to create new columns to have those specifically. So that's what I'm doing here. And I'll walk through this in just a moment. Okay, so this was a little bit more complicated step for the parsing. If you remember, before, when we wanted to do the daily cases and the daily deaths, there was this whole thing about, making sure that we isolated a specific county. And then in the base version, you could run this like for loop to go through this. But in data tables, we're doing something in a slightly more easier manner. Okay, so we want to make sure everything's in the right order. So I'm just doing order date here in the, if we remember, you have DT, comma here. So this is row filtering. And then this is column operations. So that's what's happening here is I'm just reordering the data set by date. And then here, this dot is this analogous to list, as I was, as a reminder before. That's why there's a period there. And then I'm just saying, okay, in this new thing, table that I'm making, make sure to bring in the date column, the state column, this FIPS, cases and deaths. And then I say, okay, I'm going to also make this new column, cases.daily, which is equal to 0 and diff. Diff is the thing that subtracts the previous row. And then that's going to give you one less entry. So I'm starting with a 0. So then these will be of the same length. So I'm doing that for cases.daily and deaths.daily. And then I want to do that operation all by county. So I have this by at the end. This is the group by operation. Okay. So I'm going to run this guy. And then I have, I'm going to do 2 new columns really quickly, and I'll describe what's happening here in just a moment. Okay. This is probably going to be pretty confusing for folks. But let me describe what is happening here. And I think the best way is actually to show you. So I think it's more valuable to understand what I'm doing as opposed to just seeing what the code is. So I'm going to go back to the code in just a second, so don't worry. Essentially, I have these FIPS codes here, okay? And okay, let me tell you my objective here. I have another data set, which I'm going to pull in just a second, which is from the census. And I want to draw in the population. And I want to be able to like have a row, which will tell me all this information here. And then I want an extra column that gives me the population of that county. And so that might be useful for me to do like per capita things, okay? So eventually that's the goal here, to do these visualizations and have enough data to look at a couple interesting things. So that's what I want as my end product. When I look at the data, I'm going to notice in the census data that I have a column with a FIPS code for the state and a FIPS code for the county. Okay, And so what I'm gonna end up doing is I'm gonna merge these two data sets based on those two columns, okay? And so I have this FIPS code that has the combined FIPS, and I wanna split it out so that I can do my merge operation. So all that stuff that I was just typing is code that will generate these two new columns and kind of split this up. Okay. Again, we don't really need to get into the details, but basically what I'm doing is I'm grabbing of the FIPS number, I'm going from the first value, this 5, to the number of characters in here. So there's 5 total minus 3. So in this case, it's going the first two, and then it's going to grab for the county one, everything minus 2. So there's 0 to the 1. So it ends up being 61. Does that make sense? I'm basically taking it and splitting the FIPS code into these two columns. That's what these two lines are in the code. And so, yeah, if you want to take some time on your own and dive into that to see exactly what's happening I encourage you to do that. But I'm kind of just wanting to explain qualitatively what's happening here. Okay, so let's pull in that census data, which is that other data set. Okay, so here, that's loaded in. We can take a quick look at that, although what I will say is that sometimes you're going to have data that looks like this. And there are 100 variables here, and we don't need all of those. Really, the only one I care about is the population. So that's what I'm going to bring in here. All right, so I am going to do my merge operation. Okay, so you merge X and a Y. So my X is going to be my COVID table, and my Y is going to be the census table. But in this case, I only care about, I only want my population estimate. So that's one column. And then I'm going to need two other things, which are the state and county ID columns I was just telling you about. And that's what I'm going to do my merge on. Okay. So these are the three columns. They're called state, county, and then pop estimate 2015. Okay, so this is where you have the by argument. And in the class example before, we had the column names of my X and my Y be the same. But in this case, they're not, right? Because in the census, they're called state and county, but in covid.dt, they're called fips.state and fips.county. So if you remember, I gave, I think, one example of how to do this. We have by.x. So we'll put the names of the columns from X in here and the names of the column by.y in here as well. So state, comma, county. Okay, so this should perform the merge operation. So I'll go ahead and run that. And hopefully what we'll see if I jump back to my covid.dt. Great. Okay, so now you should see that I have an estimate for the population in 2015 for each of the particular counties. Okay. Yes. Yes.
So does it internally do an image join or the?
Yeah. So check the notes. I try to walk through this very thoroughly. So there's 4 types of merges: left, right, inner, and outer join. The default here will be an inner join. Okay. Okay, so what I'm gonna do now is, I think we're kind of primed to do the plotting now. I think the data is at a state where I can now start to do a little bit of plotting. And I'm kind of freestyling this portion. So what I'm gonna do is I'm going to show just one example, and I'll kind of walk through the code here. And then I'll ask you guys to think about, so already right now, start thinking about some possible visualizations of this data, and then we can kind of work on it together. So, this is what we were working with, right? We've got county by county, daily measures of cases, deaths, cumulative cases and deaths, and the daily cumulatives and deaths across the US. So think about some things that you might want to visualize, right? I mean, I can imagine dozens and dozens of things that we can sort of already look at. And don't worry about any of the coding, just think about what you would like to visualize. So let me talk through the first example that I'm gonna do, which is, let's just look at cases, daily cases of coronavirus in Yolo County. Okay. So we're gonna use ggplot, as I was mentioning. And there are, so this is a function. This function here sort of initializes everything in the plot. And there's 2 things that you pass into ggplot, okay? There is the data that I'm gonna be plotting on, and then there's this thing called AES, which is the aesthetics. Okay, so before I even fill this in, let's talk about this visualization that I have in my mind, and what that's gonna look like on the graph, sort of irrespective of the data, right? So I said I wanted to look at daily cases of coronavirus in Yolo County. Okay, so who can tell me what would be on my x-axis? Dates, exactly. So dates, and what would be on my y-axis? Number of cases, great. So number of cases. So that is what you tell the aesthetics, okay? This is why it's really important to do this first and then get into the code. So it's pretty simple here. AES parentheses, X is, okay, the dates. So let me put that in. Is it date or dates? It is date. Okay, so date, and y equals, let's do cases dot daily. Okay, and then the data is going to be equal to data equals COVID.dt, but I only want Yolo County, and you can do this separately if you want and define a new kind of object, but I'm just doing it here. County equals YOLO, like such. Okay, so this is the initialization of my plot, and then I can start to layer in options. So the one mandatory one is geom. Okay, so geom specifies the type of plot that we want to see. So in my mind, I think I want to see this as a line plot, okay? So all I do is geom underscore line, and that's it, okay? So let's first look at this, and then I'm gonna start layering in some other options, but let's see what this looks like first. Okay, great. And so if I just ran these two lines, I would generate a plot that looks like this. And these are my sort of daily cases of COVID in Yolo County. Okay. So let's take a look at some other things that we can do. I can visualize this also as just like a bar plot as well, okay? And so instead of a line in each day, you have a bar. How do you do that? Pretty simple. Instead of doing geom line, you say geom bar. Bar has some slightly more complicated options. I need to do stat equals identity. Yeah, so okay. What geom bar is a little bit more complicated than some of the other ones because it can do things like it can count your data for you. So I'm just saying the numbers that are represented are the actual like counts already. That's why I have this stat equals identity. Don't worry about this too much. You'll get used to some of the nuances of bar, but let's just look at what this looks like. Okay, it's almost like the same thing, right? Except each day is represented as a bar instead of like a connecting line. So you still get a sense of the pattern. So you can do all sorts of crazy visualizations here. Line and bar are probably the most common ones that I use, but there's a couple other ones that are context specific. But all of the modifications of like what this stuff in here looks like is based on what you decide to put in for geom bar or in the geom. Let me go back to the line, which is kind of what we mainly want to work with here. Okay, so let's try and layer in a couple other options here. Let's say I want to clean up my axes a little bit. That's pretty easy to do. So I can do xlab, which stands for label. So let's just capitalize date. And then ylab, let's do cases of, or let's do daily cases of coronavirus. Okay. So we'll run these guys. And you can see now that you've just changed the labels here, right? I can add a title to the plot. I believe is it GG title? I think so. Yolo County. OK. And you can see it prints that up sort of at the top, and there are options where you can kind of move that around. If you want to put it centered or on the bottom, whatever, there are options to do that. And then there are some themes that you can do to make it look a certain way. So I typically use theme BW, black and white, which ends up looking something like this. So it modifies the plot a little bit. Does anyone know any other themes? I always forget in ggplot. Classic? Yeah, that's right. So another one that you can do here, classic, looks like this. So this, you can see, gets rid of the axes lines. And all of this is actually sort of really customizable. You could like leave the horizontal axis lines or the vertical ones if you want. But these are kind of some of the built-in ones, so you don't have to go through a lot of those options manually. And yeah, and I'll let folks kind of explore some of those on their own if they want to mess around. This is like one of the most popular visualization packages in R. So there's a lot of online resources and other tutorials, which I'll post in the notes that you guys can take a look at if you're starting to run into any issues with this. Okay, so let me go back to this one. So, okay, oops, don't want to save yet. Yeah, so that's the basic kind of structure here, is that your initialization and then the geom is going to get you like 99% of the way there, and all the rest of this stuff are basically options that you can do to mess around with the chart, except with the exception of one last thing, which I'm going to talk about right now, which is one of the more powerful things that ggplot can do. Okay. Let's say, I'm going to delete this guy. Let's look at a plot of both Yolo County and, let's say, Sacramento County. So in my filter, I'm going to say both Yolo and Sacramento. Okay. Okay, wait. Before I do this, there's one quick option that I wanted to mention here. You can, I don't actually recommend doing it this way. If you want to do this, you should do it in the data, but you can set a limit to the data ranges. Okay, for dates, how would I do this? So xlim means that I want to set my axes to a specific range. And so you would usually do, start, comma, end here. And then what you would see on the x-axis begins at what you say as start and what you would say at end. I'm getting myself into trouble here because I don't know if this will work, but let's do this. O3 slash, maybe this works. No. Okay. Oh, oops. I have a comma there. Please work. Oh, yes, wait, did it work? No. Whoa, what the heck is with that date? Okay, one last try. Percent M dash percent D dash percent Y. I don't often do this. This is why it's usually better to do this in the data than to do it here, but let's give it a shot. No, no, no. Oh, okay, great, sweet. Okay, so basically, instead of going from the full range of like whatever, February 2020 to March 2022, I just said, don't let it go. I want it to be between January 1st of 2022 to March 1st of 2022. And you can see what that looks like here. Okay, so that's one way you can filter. Again, I highly recommend that you do this just from a good practices sense to do it prior to this. I think it's better practice to kind of manipulate the data first and then just cleanly make your ggplot without manipulating the data kind of in ggplot, but you do have that option. Okay. Yeah. So you're saying here?
Yeah.
I would do it like and date. I would say greater than year 2021, something like this is what I would do. But you need to oops. I would need lubridate to do the as year function. And then I would get rid of my xlim. Oh, whoops, that's up here. Yeah, I would, let me comment this guy out here. And let me put this in here. Yeah, so in the filter, I would do something like this. No, I keep auto saving, sorry. Origin must be, okay, what the heck does that mean? Oh, whoops, wait, date, sorry. Year of date should be greater than 2021. So yeah, if you want to do it in the filter, this would be what it would look like. This is a little bit more because this includes March, but you can mess with that as well. Yep. Okay. So this time I want to plot everything, but I want to plot both YOLO and Sacramento. So what I've done is I've created this filter here. Instead of equal to YOLO, I'm going to say percent in percent, which is telling you to look at multiple values. So anything that has county equal to YOLO or county equal to Sacramento, it will grab that data and we're going to plot it. Okay, so what is this going to look like? It's going to look crazy because, okay, you can't even see it here. Let me do, actually, let's do that filter so we can look at it a little bit more closely. So, and year of date, say equals 2022. It's gonna look crazy. If it runs, oh, did I not run it? Okay. Can we see the craziness happening? Why is it not? Well, okay. What does it even mean to plot two things at once? So essentially what you should be seeing is something like this. So day, county, and then cases. So you have day 1, 1, 2, 2, 3, 3. So you have 1 for YOLO, 1 for SAC, 1 for YOLO, 1 for SAC. And then, you know, X, Y, Z, A, B, C, okay? So on day 1, you actually have 2 data points. You have X and Y. So here, instead of this, you will have something like this, and then the plot will look weird, or it should look weird. It'll have probably what's happening actually is that YOLO is always lower than SAC, so you're always going to have some kind of thing that looks like this, yeah. And that's not what we want, right? So I can actually do this neat thing called facet, which lets me break things out into groups. So there's 2 types. You can do facet grid and facet wrap. Grid is going to let you do kind of multiple dimensions. So we'll see what that means in just a second. So I'm going to do county like this. Cool. So just by doing this, I am able to visualize Sacramento and Yolo County separately. And you can do this. This is really powerful. Okay, this can separate this into many, many counties. So like if I wanted to do California, and I wanted to look at all the states or all the counties in California, watch what happens. So exact same code. I'm not even going to touch any of the options or anything. All I'm going to do is change my data filter. I'm going to change this so that I do state equals California. Does anyone know how many counties there are in California? Probably more than we should be plotting here, but 58. Cool. There they are. You can't see anything, but Facet does this all automatically for you, which is pretty neat. Imagine doing this in Excel, right? To produce 58 plots, it would be a pain. But here, I literally didn't have to change any of the code in ggplot. It's just what data is going into it. So pretty powerful. Okay. What do you guys want to see plotted? You can get as complicated as you want. We'll see if I can pull it off right now. Anyone? Throw down the gauntlet. Let's see here. If I go back to this guy, I'm going to change a couple things. So I'm kind of like freestyling here. Oh, yeah. By age group. So we could do that if we have the data, which I guess technically we do in the census database. But I don't know what those columns are right now. Based on what we have, is there anything that you guys would like to see? So continue thinking about that for a hot second. One of the things that you should be thinking about when you start going through and making these plots is like getting feedback from what you're producing to see to get new ideas for plots. Okay, so here I'm already thinking about some things. Okay, if I look at these guys, so from a sort of visualization perspective, right? There's nothing wrong with this plot, especially if the point of the plot is to show like a comparison in magnitude between these guys. And from there, I can really clearly see, oh, okay, like Sacramento has had way more daily cases than in Yolo County over, this time period in 2022. So this kind of chart would be a really good example of doing that. But if I wanted to look at something else, is like, oh, maybe I want to look at the relative shapes of the daily cases. Well, this probably is not a really great visual representation. You have a lot of white space, right, that you can do. So what I'd like to do is actually have these both show separate axes. Okay, so that's an option that you can do in facet wrap. And that is simply by doing this. In the facet, you do scales equals free y, which will allow each graph to have their own sort of y-axes instead of linking them all together. And this is like, okay, obviously you wouldn't know this, right? But this is something that's really kind of easy to look up. And there's a lot of resources on this. So, okay, so if I run this, okay, now I can see, oh, actually, the shapes look really similar now that I've kind of filled in that white space and I allow these guys to be on separate axes. So actually, maybe Yolo County was doing just as bad as Sacramento because the shapes look the same. Is that true? You're shaking your head. Why would that be the case?
Well, I think the main issue is that those have completely different y-axes, but they also have different populations.
They have different populations. Great. Okay, so how can we standardize this? Yes.
Do it per capita.
Per capita. Great. All right. So why don't we do that? Okay. I'm going to delete these scales, right? Because we say, okay, there's different y-axes, so it's not a fair comparison. So all I'm going to do is cases daily divided by what was it? Pop estimate 2015, I think was the name of the column. So this divides the cases by the population. So you now get daily cases per capita. Cool. And without even having them on the same axes, right? Notice here, I deleted the scales equals free y. Now they're on the same axes. And actually the relative magnitude is pretty similar. Okay, so on a per capita basis, okay, so now what would you say? Is this a fair comparison?
Much more fair.
Much more fair. And right, they look pretty similar. So in that case, we can say, okay, on a per capita basis, maybe Sac and Yolo County look actually pretty similar in terms of number of cases. Yeah.
What are we talking about the drop weekend?
Yes. Okay, yeah, we can do that.
I'm looking at these charts and I'm seeing we bottom out what looks like every week.
Drop weekends. All right. Labor Day, day of week. Yeah. No, we can do it. I said to make it challenging. Okay. Let me see if this is what I want. Wait, covid.dt. I don't actually know if this function is what I want, so I'm going to test it out here. Okay, it is, but I don't know what day it starts on. Give me 1 second. Oh, okay, so it's Sunday. Okay. So 1 is Sunday, 7 is Saturday. So let's do it without the weekends. Okay. And so basically to do it without the weekends, I'm going to add a little filter here. So I'm going to say, and weekday of date is not equal to, or actually since it's going to be multiple things, I'll do say %in 1,7, and I want this to be not true. So not weekday in 1 or 7. So this gets rid of the weekdays. It's going to look a little weird. Yeah. So this is what the plot will look like. Per capita, daily cases, not including the weekends. Looks like this. Yeah. What else do we want to look at? Anything?
How do you forward this? If you want to see like this is the number of cases and out of this is the deaths.
Sorry, what?
Or one single plot have both the cases and deaths.
Oh, yes. Great. Okay. Yeah, there's lots of ways we could do this. Let's do, okay, so why don't you, so before we touch the code, why don't you describe to me what you'd like to see here? So start with this. What do you want to see on the x-axis? Dates?
Dates.
Okay. And what do you want to see in the y-axis? Yeah, so number, okay, so cases. And then what do you kind of imagine you would see in here?
A lot of cases for daily cases, but the deaths are going to be not true.
Yeah, okay. But you want to see 2 lines, basically. Yeah, so we'll have a cases line, and then we'll have a deaths line. Okay, so this is actually an alternative you can do to the faucet, which is we're dealing with multiple dimensions. I could have had 2 different lines on the same plot, right? So that's what we're going to show here, is a different way of folding in multiple variables or dimensions into the plot. So Okay, this is going to be our last example for the day. So ggplot. We're going to do data equals. Should we do the same thing? We'll just look at Yolo County. Okay, so actually, let's not do Yolo County because I don't think there's going to be, well, it's a little morbid, but I guess you want to see some action in the deaths. Let's actually look at a state. Let's just look at California, for example. So data equals COVID.dt. Okay, we're gonna run through this really quick. State equals California, and I'm actually gonna do some manipulation of the data here. So date, I want to include, and then we'll do daily dot cases equals sum of daily dot cases, and then daily dot deaths equals sum of daily dot deaths. And I want to do this comma by equals state. Okay, so then actually let's do two states. Why don't we do that? State percent in California, and let's say New York. Yes, okay. X equals date, Y equals oh. Okay. This is actually a case where we're technically actually in a slightly wide data set, and I would ideally want to turn this into a long data set so that I could have daily deaths and daily cases in the same column. That's the ideal way we would want to do this. But so for the purposes of right now, because we're a little short of time, I'm going to hack this a little differently. So you can actually specify AES in the geoms as well. So anything in the ggplot is going to apply to the rest of it, but anything that you do in here is going to just be for that particular geom. So I'm going to have two geom lines instead of one to create two lines. Ideally, I wouldn't do it like this. Maybe at the beginning of class next time, I'll show how to do this kind of properly. But for now, I'll just show how to actually do this. So AES, X equals date, Y equals daily dot cases. Let's make this guy red. And let's make the other guy blue. X equals date, Y equals daily dot deaths. Color equals blue. Okay, I'm not going to do any formatting. Well, I'll just do this really quick. And then facet wrap by state. Okay. No. Is it cases.daily? Is that what it is? And this is deaths.daily probably. Okay, go, go, go. Whoa. If I sum, oh, wait, sorry. By dot date and date. Okay. Okay. That doesn't look quite right either, does it? Okay. I blame it on being rushed. I'll make the plots. I'll go through this at the beginning of class next time for this particular example. Just ignore this last bit. Thought I could do it. Okay, great. So next class on Thursday, homeworks are also going to be due end of day on Thursday. So make sure to get those in. Everything has to be submitted as a R Markdown. I gave the example file last class, so make sure to check that out. And just, yeah, come to office hours if you have any questions.